Yeah, well, thank you very much. And please don't hesitate to interrupt me if you don't understand anything or if you have any questions at any point in time. Um, it's going to be, hopefully this will be a constructive and a learning experience, and it doesn't need to be very formal in that sense. So just don't hesitate. Um, just a brief introduction, first of all, about myself. I'm a hydrogeologist. A geologist initially by training in the mineral sector, moving into humanitarian work for a few years as a WATSAN engineer. Worked for MSF for a while as part of different organizations, and then moved into hydrogeology, where and then about 10 years ago set up Groundwater Relief, which is a charity, UK registered charity that provides groundwater expertise specifically to the humanitarian sector. And we do that through a membership of about at the moment 600 groundwater experts from across the world. So over the course of time, we've had to undertake many different types of groundwater investigation, and obviously to support borehole siting, but also looking at water resource management and uh, sustainable management of those water resources. So and that's also involved things like remapping the aquifer systems, because many of the places that we're working in and which you're working in, there is a limited amount of information about the subsurface. So the purpose of this sessions today is to talk specifically about the challenges of borehole siting specifically, and looking really at the context of working with in places where there might not be very reliable contractors to support borehole siting works. Now, I'm aware also that there's a continual challenge about contracts with these with drilling contractors and water supply, and how often it's a case of just putting risk onto the contractor to get the water required, the kind of pay by result, and therefore you have very limited if you're putting that kind of contract onto contractors, then you obviously have very limited a power or ability to influence how they actually decide on where to put those boreholes. But there's, apart from your site footprints, etc. So there's lots of conflicting. But in other cases, you might have separate contracts between the borehole siting and the drilling, in which case you obviously want to keep you want to know that the work that's being carried out is of good quality. I'm going to just jump in with the first session, but which is basically going to be about an introduction into the core concepts of borehole siting, to give a sort of overview picture to help us with the rest of the day. So let's share my screen and see if this is going to work. Can you see my screen?
Yes.
But and is it on full screen for you?
No, it is.
Okay, great. So for this first session, we're going to basically introduce the fundamentals of borehole siting with looking at different geophysical approaches, but with a focus on really electrical resistivity methods. Just for your information, at the end of this day, all the slides, etc., information I will share, as well as some background reading information, etc., if you're interested in exploring more about the subject. So don't worry about that. When we look at the siting of boreholes, the primary hydrogeological constraint is the geology, and there's generally three broad siting scenarios that we encounter. There's the easy to find groundwater in sedimentary aquifer systems where you have layered, quite homogeneous systems where basically anywhere you put a borehole, you're going to access the aquifer system and the water resources. And in these particular scenarios and cases, it's more about the borehole construction than the siting. So the actual where you put the borehole can be anywhere that's convenient. It's about how you then construct the borehole afterwards. There's exceptions to that rule, of course, when you're looking close to the sea or where there might be saline water, in which case it might require further investigation work to make sure that you're pumping sustainably fresh water rather than bringing in saline water. In many parts of Africa and other places where there's dominance of crystalline basement rock, then we run into this second scenario where the hydrogeology is very well understood. The geophysical methodologies for siting boreholes in this kind of geology are very reliable, and so this is actually where geophysics becomes really, really useful. And then the third scenario is where the hydrogeology is very complex and poorly understood, and this becomes a challenge for hydrogeologists in general. It certainly becomes a challenge for drillers and local hydros too, and really requires a lot of detailed modeling and investigation work to start to bottom this out. So that becomes far more expensive and challenging. So the focus on this training is about where you would be quite often using a geophysical contractor with simple basic equipment, i.e. a terameter doing 1D vertical electrical soundings and hopefully constant separation traversing, which we'll talk about in a second. So this is our focus on this kind of geology, where it becomes really useful to help improve your outcomes when drilling boreholes. The amount of money that you invest into the siting of boreholes will depend on the geology, but it will also depend on other aspects of your program, including how much water you require. Obviously, greater volumes of water required add to the risks and the challenges, which means that you probably need to invest more in the exploratory work first of all before you contract out the drilling works. It's obviously very dependent on your physical constraints. If the only real options for you is to drill a borehole in a particular compound, then there's very little point in investing in initial investigation work, geophysical investigation work. You might as well just drill a pilot borehole and see what's down there. And then the water quality risks, and of course the drilling costs itself. In some places, drilling can be extremely expensive, in which case it might be economic to invest in a geophysical survey first, just to improve odds of getting a successful well. What we're going to be talking about now is when contracting out borehole siting works, you should really be expecting prior to the field work that's carried out that a desk study is initially undertaken in order to conceptualize the subsurface and to therefore, with that conceptual understanding, create a geophysical field plan, a program that before the field work is then actually undertaken. When we talk about desk studies, we're talking about bringing together existing information, which might include historical data sets, literature, existing geological maps, soil maps, hydrogeological maps, and utilizing remote sensing information as well. It might be something that you do prior to contracting out a particular geophysical company, in order to sort of inform on what works you're going to then take forwards with a particular contractor. So if that's the case, then there's a large amount of information out there. Even in the most remote areas, it's surprising how much data that you can get hold of in terms of at least basic geological maps, using some remote sensing information to give you a preliminary idea about what type of investigation work you're going to need to engage with. Types of actors that you might want to approach if you're going to be doing that kind of thing would include local drilling contractors, mining companies, and obviously the ministries and any local universities, etc., that might have data that will be very helpful for you to get a general idea of what's below your feet. Remote sensing data is useful because it's worldwide available, and there's a lot of free sources of information that can be utilized straight away. When it comes to borehole siting, things haven't really changed very much, even with this remote sensing data, since 100 years ago. What hydrogeologists are looking for when they're looking at siting wells is they're looking at structure within the rock, and the drainage patterns of recharge that comes with that structure, and then vegetation, which can be quite indicative of water. So the key remote sensing data sets that you can use and engage with directly is first of all digital elevation models that provide you with an elevation map for an area and shows you structure straight away, which can be very helpful for planning out any kind of survey, which we'll come to later on. Obviously, with the structures, as well as in a crystalline basement rock setting, for example, as well as those structures being potentially sources of water in terms of transmitting water to your borehole, they're also likely to have resulted in deeper weathering profiles in those areas. So water obviously flows downhill. It also flows down these deeper weathering profiles underground as well. And if water's moving, there's chemical weathering that's also taking place, and often systems will be becoming more open the more water that flows through them. So historically, people will locate boreholes at the base of a valley because that's first of all where the recharge is happening, but also where there's likely to be more transmissivity and more storage potentially if you've got deeper weathering down there. When it comes to vegetation, satellite information can also be very helpful in terms of looking at multispectral optical data sets, and false color imaging is probably the most classical way of using those kind of data sets, where you're looking at the sort of higher vegetation areas. And the great thing about these data sets is that you can use, you can obviously look at how vegetation changes through time, both in the rainy season and the dry season. And with more powerful tools now available like Google Earth Engine, AI tools, you can really start to deeper analyze this information to try and pull out the extremes to help you with understanding where recharge might be occurring, where there's a continual permanent water source available for vegetation in a particular area. All the information that you pull together, you would put onto GIS mapping. GIS is a highly useful way of comparing spatial data sets, and that would all lead towards development of your conceptual model. Conceptual models are actually quite easy to do yourself. They're very useful processes just to try and help with understanding of the place you're working in. How you draw a conceptual model is that you would sketch it based on any information that you have, including topography, geology, any water point data, any water level data, and then you would start to just think about how it might be working the system below your feet. So the way that we would normally draw a conceptual model of a particular location is we would first of all use Google Earth to create a sort of topographic profile that we could then start to annotate. And the more information that you have, obviously the better the more information you have, obviously the better you can draw your conceptual model. So this is an example, for example, in Burkina Faso, where certain borehole records were able to be utilized to start to actually map the potential differences in geology and the weathered zone and where the water level might be, based on a few records and based on then that elevation profile taken from Google Earth. And you can see how just by plotting this type of information on to a conceptual into it, sketching it out, then can really help you start to decide on how you might then, where the water might be, and then how you would go about investigating that, getting more data perhaps through geophysics potentially, in order to confirm that model. You can build conceptual models using more sophisticated software as well. We've have access to a software called Leapfrog, which is a geological modeling software. So you can then, you can use then, you can plot some borehole records on and start to create a 3D geological model. But there's nothing wrong with just a simple conceptual model sketched on using PowerPoint or something like that. Where you might have limited data, you might also want to increase the amount of information you have to build on your conceptual model, and that can be done through a basic field survey, which would include going to the existing water points, dipping water levels in those water points, measuring the depths of the wells, taking basic water quality samples using perhaps an EC, electrical conductivity probe, literally mapping out any outcrops you see, describing them, talking to the local population about reliable water points, less reliable water points, any problems they have where they go to get their water, etc. And by taking this kind of information, you can start to plot it out onto a map, a reconnaissance map. So in this particular, this is an example from one of the literature books that will provide. But in this particular case, you've got an initial geological map that then somebody's driven along and taken notes about, so making just outlining on the roads what they're seeing in terms of the geology. Then they are putting extra notes on, like in this particular area, there's lots of abandoned boreholes. Here, there's a low-yielding borehole. There's a good hand-dug well there. This type of area has got very difficult to find water. Here's a great water supply in this particular point, and then from all of this, they're able to determine, in a way, where the good aquifer system is, where there's very little chance of getting water, etc. And where they might be chances to get some water, but it might require some more detailed geophysical survey work in order to get it. So you can see how this kind of activity can really help you then when you're looking at, in the end, going forwards with contracting potentially out somebody to then do the field work to actually help you with the water supply. So based on the desk study work that you pull together and those sort of initial outputs, that might then lead you towards planning out the geophysical works if you're doing it yourself, or deciding on who to contract out to do the geophysical works. When it comes to then getting the contractor, if you're going to use a contractor what you'd really like to see from them, as I said at the beginning, is a work plan from them outlining what kinds of actual geophysical works they're going to do. And what you'd hope to see from that is that they are basing those decisions on a clear understanding of the subsurface. So I'm using this as a case in point, but I mean here's a field plan carried out to do a geophysical survey for a water supply for a hospital in Central African Republic, and by plotting out likely fracture areas in this particular geological type, it was then possible to plan out where surveys would be undertaken in order to try and intersect with those fractures, as a way of an example. And here's a couple of different types of scenario here's a conceptual model of a basement rock setting, and you can see that within this conceptual model, you're going to have a far more better chance of getting water where you have a deeper weathering and possible fracturing compared to an area where there's very shallow weathering and potentially less fracturing. So when you're doing an investigation work in this kind of scenario, you're obviously wanting to look for areas where there is deeper weathering, and that will then inform on where you can. So if you can find that out through the geophysics, then that will then really help you with developing a better water supply in this kind of basement rock terrain. Here's a slightly different environment within schists. So in this particular case, although there might be deeper weathering, that area of deeper weathering might be very it might comprise mostly of clay, because the schists will break down into clays without any quartz sands. And so in this particular case, you might actually be looking for these zones of deep weathering, but actually wanting to be drilling below those zones of deeper weathering in order to intersect with the fracture that caused the deeper weathering in the first place. So are there any questions so far with how to develop a conceptual model, looking at some initial, and in the importance of doing that before planning any kind of geophysics work. Is there any questions yet on that before I move on?
Me, I would
maybe
like.
one.
Oh, sorry, go ahead, Olivier.
Yeah, sorry, I don't know if it's a question or a comment, but when I try to bring this down to a context where, for example, we have a hospital setting in, for example, a 200, 300, or say a 400 square piece of land, if I understand well, your suggestion is, in as much as we have just that small area, we should try to expand the investigation to be able to get the best out of it. Correct? Because we tend to always want to focus around inside of the premises where we are, and sometimes doing this investigation on a small scale could be challenging. What do you think about this?
Yeah, no, I mean it's a real challenge because you've got I mean, if you've got a very restricted site footprint, then you have to determine how useful it's going to be to do any kind of investigation work, rather than just going ahead with drilling a pilot well to see, or drilling a well directly. 400 meters doesn't sound like too restrictive. That seems like you've got some area to peruse on that. It would depend on the geology straight away. So if this is a specific example, do you know if you know what the geology is, if it is a sedimentary system, obviously it won't make any difference at all. You could drill anywhere on that compound area. If it is a crystalline basement rock setting, then 400 meters might make quite a bit of difference if you drill one side of the compound to the other. And in that particular case, you might then still consider doing a geophysical investigation around the compound in order to try and identify structure that might be crisscrossing into the compound. Does that make sense?
Yeah, yes, fine for me. Thank you.
Any other questions? Yeah.
Yeah, Sebastian is.
Yeah, it's just a remark about the geology map. We used to work in a very sensitive, a super place where land are, you find gold, you find very bankable mineral, and the geology map are sensitive. You cannot ask the university will tell you, no, this is sensitive map, you should not have it, etc. So what do you think about that? It was the case in Congo, Ituri, all these places.
Yes. No, I mean, so data sharing is often a challenge, but I would go beyond then the university or whatever it might be. I mean, you can't obviously force people to give you information, but in areas where there's a lot of mineral wealth, there's actually a lot of data wealth too in general, and there might be aerial magnetic surveys, aerial geophysical data that's been collected for that area because it's has got mineral wealth. Some of this information is accessible. It might cost a bit of money, but it is accessible. And then I would also go to if there might be other geological surveys outside of the country that also might have geological maps. There might be libraries outside the country. So if it's an ex-French colonial country, I would go to the BRR, which is the French Geological Survey, and I'd also perhaps approach French universities or French libraries and see if they've got the information that might be available as well for that area. So, I mean, it's frustrating that people aren't sharing geological maps when they have them there in there, but there might be alternative sources, and certainly in mineral-rich areas, mining companies themselves you might look at historically what mining companies have been operating in the area and approach them directly, and there might also be quite a wealth of aerial geophysical data
have another question. If this one, Sebastian, is that good for you, the answer?
Yes. I mean, there is a lot of information on the land, of course, because it's very bankable land, but it's not accessible easily. They refuse. This is the point. So, but let's continue. Yes.
Yeah, just wanted 2 minutes. I mean, because you were talking about schists being like the weathering, all clay, and then so you try to really go to the crack, I mean, the fracture that you have underneath, as compared to granites, they might be more sand around, so then you have more leverage. And so would you just expand on that?
Yes, yeah. So different different hard rock can have different characteristics, weathering characteristics. So it's good to know what those weathering characteristics might be. I mean, it's that not just for the borehole siting works, but also because often the borehole siting works might go hand in hand with the drilling works itself. If you're going to be putting that risk, as I mentioned at the beginning, directly onto the contractor to do the borehole siting as well as the drilling. So taking that particular scenario, where you might be looking to want to drill deeper in a schist rather than in a weathered granite, where the likely main water source within the granite will be at the rock head, where you've got that, where you've got a lot of quartz, sands, etc., close to that the basement rock setting. Well, in a schist, you will be thinking we can't get that there, so we'll have to go deeper to try and intersect with fracture systems in the actual hard rock of the schist itself. So it could also inform on, I guess, your actual contract in terms of the drilling depths and works as well.
Okay, great. Thank you. Yeah, I think there is no more questions, right? Can move forward.
Oh, great. Well, I'll move on then to basically give a very brief overview of many of the different geophysical techniques that are available out there, focused on the ones that we see as being most important for water supply and for water investigation work. So geophysics is a way of measuring various physical properties of the subsurface to better understand it. But I'm sure a lot of you have encountered this yourself. It's often very poorly undertaken. And the most common method is 1D resistivity, which is actually the focus of this day. However, there are many different types of geophysical approach, but quite a lot of those might not be accessible through local contractors in areas that you're working. So, but it's good for you to be aware of them anyway. And we have in the past brought in experts from overseas or different countries to support local contractors with perhaps improving the way that they carry or using a different technique other than the equipment that they have. So when it comes to 1D resistivity, you have two key approaches with using this 1D equipment. There's the vertical electrical sounding, which we're going to be talking about in a lot more detail later on, and there's which is basically where you're taking a measurement from one point on the ground, but then expanding your electrodes outwards to get a depth profile, so a sounding. And then there's the alternative is to move the equipment along a lateral line in order to get a transect, which then shows you variations in apparent resistivity laterally. So that's called a constant separation traverse. Generally, with electrical resistivity, you're looking at a kind of maximum depth of about 100 meters. You can go deeper than that, but then you're going to have very large arrays and larger power. So in general, with the contractors that you're engaging with, the top 100 meters is probably the kind of penetration that you're expecting. Another technique that also looks at the resistivity or the conductivity of the subsurface is something called electromagnetics. This measures basically apparent electrical conductivity of the ground. It's got by inducing a magnetic response. It's quite practical in the sense that you don't need to put any electrodes into the ground. You can actually go at a lot quicker speed and go across roads, etc., without any problems. But it's got a different depth penetration. It's a bit shallower. It's about 50 meters, and so it's more useful for looking at lateral variations in geology rather than looking at depth. Another electromagnetic technique is called transient electromagnetics. This is where you're pulsing an electrical magnetic signal into the ground and then measuring the response from the ground from that. I'm going to talk a little bit more in detail about it in a second, but it's I suppose the key point in this is that it can go to much deeper depths, which is very useful. It goes much deeper than it can go deeper than electrical resistivity as well as electromagnetics. And it's a useful tool for for hydrogeologists. You can also use very low frequency geophysical techniques, which is a passive technique, which basically is using induced secondary magnetic fields that are happening due to transmitters, telephone transmitters, etc., creating these induced fields within the ground, and it just measures those. And it's quite useful for locating fracture zones and dikes. I've not had any experience with that myself, so I can't really talk much more about that. Then we can go into seismics, which is where you're actually creating a sound wave through the ground to measure that sound wave velocity as it passes through the ground. It's obviously an approach that the oil sector uses quite a lot. It can go much deeper into the ground, although I'm not sure why it's got 30 meters there. And then we have magnetics, which is using the Earth's magnetic field, and ground penetration radar, which is more used in a contaminated land setting, or looking at engineering for holes in the ground close to the surface, which might cause buildings to subside. And finally, there's gravity surveys, which I've never seen used for as a primary water supply survey. So going to 1D electrical resistivity, this is where you have a terameter, basically, which is a piece of equipment that is collecting the information, and you're connecting that to a battery as a power source, and then you're connecting to the terameter some wires that will pass the electrical signal that the terameter provides, the current that the terameter provides, into the ground, and also collects the voltage that's from the two other electrodes. So for a 1D survey, you are using 4 electrodes, and therefore 4 wires which are connecting the terameter to the electrode, and you might have a booster to try and increase the power that the battery is providing into the signal that the battery is then providing into the ground. As we discussed already a little bit, there's 2 key measurements that 1D electrical resistivity will take. There's the vertical electrical sounding, which is where you these are the 4 electrodes here, and so you're passing current between the outer electrodes, and then measuring the voltage within the inner electrodes, and you're expanding slowly these electrodes out from a middle point within the sounding. So initially this might be a very limited distance, 1 meter either side or something like that. But then then as you slowly expand your electrodes out, you'll get deeper and deeper readings of the resistivity of the ground over depth. And the general rule is that the outer electrodes, the distance of those outer electrodes will give you between 0.2 to 0.4 depth penetration. So if these outer electrodes are at 100 meters, then you might be expecting between 20 to 40 meters, depending on the ground conditions, depth penetration based on that. And then the other alternative is that you set these at a specific distance. So for example, let's say if you were looking at a geology where you wanted to really understand more about the lateral variation at 30 meters depth, then you might well be setting these outer electrodes at around 100 meters distance, and then moving it laterally across the area of interest in order to get a lateral variation in resistivity over time. When we look at 2D electrical resistivity, it's quite similar to 1D, except instead of using 4 electrodes, we're using multiple electrodes. So instead of having a cable that connects 4 cables, which each are connecting to 1 electrode, you use a multi-core cable, which has many smaller wires running inside it internally, and each of these is connecting to a takeout, and within each takeout, you're then getting a takeout cable and connecting that to an electrode. And these arrays might have 80, depending on the type of cable that you use and the setting. It might be 80 and the company that that you've purchased the equipment of, that might be 80 takeouts or 100 takeouts, which are then all spread along distances that it will be between up to 1,200 meters length. We've used in Bangladesh, for example. So over a kilometer of cable spread out with these electrodes attached at takeout lengths of between 5, 10 or 20 meter distances. How it works is exactly the same as 1D electrical resistivity. It's just that because you've put out a lot more electrodes, you're able to take a lot more measurements. And this is so how it works is that each of these is a takeout that's been laid out within the cable. And then you've programmed the machine to start to take measurements, and then it will take measurement after measurement after measurement, just running along. Running through different scenarios where it's starting to extend out the electrodes it's passing the voltage through, the current through, and the electrodes that it's measuring the voltage from, until you're able to get to quite deep depths at the when you're using the far outer electrodes and the far inner electrodes. So that might collect over 100, 200, 300, 500 types of data points within one line, which enables you to create a 2D profile of the subsurface, and then that data is most commonly then interpreted through inversion, using different types of software, including free software like Recipe. Here's an example of a 2D electrical resistivity tomography survey rather than the 1D. And you can see that it does give a really good picture of the subsurface. So because of all of those extra measurements taken, you're able to get a more detailed understanding of the electrical resistivity properties of the subsurface within that profile. And this is an example in Juba, where this has been interpreted, this higher resistivity area here is being interpreted as bedrock, dropping into weathered bedrock, and based on where the Nile is running, probably because of a large structure that the Nile has been running through. Here's another example of 2D electrical resistivity tomography being utilized for geological mapping in Cox's Bazar, where it was able to determine, for example, this clay layer here, because it was much less resistive, much more conductive there, and able to distinguish between the different geological formations to help remap the geology in that particular place. One other thing that the terameter that is often used for 1D electrical resistivity can do is also induced polarization. And in this case, if you switch off, if you pass a current through the ground and switch it off suddenly, the voltage between the different electrodes doesn't immediately go to zero. It takes a few seconds, and that indicates a capacitance within the ground, i.e. the ground is storing a charge which it then disperses. And so this is quite a useful technique for trying to differentiate between, for example, a clay layer which has a higher conductivity, and a water saturated sand, which also might have a higher conductivity. So if there's an area that you're working which is might have both those types of geology in the same location, using induced polarization can try and help differentiate where the electrical resistivity would not be able to. It's mostly used within the mining sector, however, to try and identify mineral deposits. This is electromagnetics is also a very common technique used for water supply. As I said before, the advantage is that you're not having to stick anything into the ground, so you can do lateral traverses quickly and cover quite a lot of ground in a day. Because of the shallow penetration that it has, it's mostly used to try and identify fracture systems, which or dikes that might be able to be picked out through lateral traverses. So you have a transmitter coil and a receiver coil, and while one coil is inducing the current into the ground, creating this the magnetic effect in the ground, the others then picking up the corresponding signal that magnetic effect is having, which then tells you a bit about the conductivity of the ground. So through this shift in an amplitude change in the corresponding signal, you can induce the conductivity. And as I said, it's got great lateral coverage. It's quite fast, so it's good for seeing near surface conductivity variations. However, some of the challenges, it doesn't go very deep, and it's susceptible also to any kind of to anything on the ground. So wires, fences, etc., will really cause problems with the signal. And you can see there's different types of instruments, and yeah, the depths that they're getting to is a maximum of around 50-60 meters. So the transient electromagnetics is probably the last one to really consider when looking at water supply. That's one of the other key ones to consider when looking at water supply, which you might come across over time. As I said it before, it relies on this producing an electromagnetic pulse, which then produces eddy currents in the subsurface. And the way that these eddy currents decay over time helps you to infer the resistivity structure of the subsurface. It's got like the electrical magnetics, there's a transmitter loop and a receiver loop. The depth of investigation depends on the size of the loop, but you can get to depths of over 200 meters with this technique, which is really fantastic when we compare that to the electrical resistivity. And I've got again, you have to be careful of potential interference from noise from surface infrastructure. But we used this technique recently in Bentiu in South Sudan, and we found it to be very reliable, and it gave us some very good results. So here's the sounding that it created based on looking at resistivity against depth, and comparing that with geology of some of the borehole records that were available. And the signal was, and there was a lot of agreement between the two data sets. And then when we compare the transient electrical magnetic soundings against an ERT profile carried out in the same location, you can see that this depth this increased depth really gave significant advantage to identifying a deeper aquifer system that the the electrical resistivity tomography data just couldn't get to. So in the Nile Basin sediments, the Thames results were far superior. So I hope that gives a general overview of the main instruments that we have at our disposal to support ground investigation work. I suppose a few last points for this particular section is to go backwards, when we're contracting out borehole siting works, I would be recommending, if you're going to be using a contractor, that they initially create a desk study that has within it a conceptual model of the subsurface and the geophysical field plan. And if you can contract them out to do the initial desk study before you contract them out to do the more expensive fieldwork program, then that will give you some confidence that they know what they're doing. If their initial field investigation plan and desk study is of good quality. The approaches that you might take to investigating or siting a borehole will be very, very dependent on multiple different, well, very, very dependent on the geology. And the subsurface is a highly variable, has a huge amount of variety and variation in across the world, and even in local areas. So by having a good desk study, that will really very much help you then choose the right technique to potentially use to actually site the well. And there is expertise which is out there, it does exist, and so I don't hesitate to get some support in order to help inform the more expensive work that might then need to be carried out when it comes to the field work. Does anyone have any questions on the on geophysics techniques, on these different types of geophysics technique? Because from now onwards, we're going to be really focusing on the 1D rather than these 1D techniques rather than anything else. Was that clear enough overview in terms of understanding a little bit more about what else is available out there? Yes, Sebastian, you got your hand up.
Yes, did you heard about this appareil named PQWT, which measure natural electricity in the ground? It's a kind of Chinese material, I think cheap and yeah.
I didn't mention. No, that's a very good point, actually, Sebastian. I didn't mention about that. I mean, I've come across now so many different types of cheap equipment, as it were, that I must admit I don't have very much confidence in. Whether there's many different types of equipment that's come through. I haven't had a chance to test them out or anything like that, but I would always fall back to the main principles, as it were, of capturing the data. And so if someone's showing you some cheap new equipment that's going to be used to site a well, I would first of all again go straight back to the fundamental of what's their conceptual understanding of the subsurface as number one, what their field program is looking to achieve, and then tell me about the equipment you're using and how that's and what properties it's actually collecting in order to inform on your plan to understand that conceptual model and understand how you're locating those zones of what you think is a better aquifer potential. So I think that would be my first point of call, as it were, is to go back to the fundamentals first of all before being having to being given this new software with new colors and new pictures, etc., that it comes out with. I don't have much confidence in any of the new equipment that's not actually, at the end of the day, sending electrical current into the ground and then getting a signal back. That's my because a lot of the, I must admit, some of these pieces of equipment I've seen being operated, it doesn't, the data that I've seen come out of them doesn't seem to make any sense to me. But I don't know this one that you just mentioned, but that's so I can't really comment on it. But does that help?
Thank you.
Yeah.
It help. As it's cheap, I think we could meet this kind of array very easily in the place we are working with the company.
Yeah.
But yeah, it look a bit. The experience I have with it is disappointing.
Yeah.
So
I mean, even really excellent equipment won't work in certain geological environments anyway. So the first thing, definitely the first fundamental thing to get is that picture of that conceptual understanding of the subsurface and what you want to get out, what you're hoping to achieve through any kind of geophysical survey. And then it would be to look into the equipment itself and to see exactly what it's measuring and how it's measuring it.
Yes, thank you.
Boris, I can see your hands up.
Yes. Thank you for the presentation so far. So my question is related to this conceptual model. You know, as most of the time in our different contexts where we are working, this part is always missing. We conceptualize direct with the company and we go direct in the deep survey using the one of the method that you just proposed. Did you think this initial, I can call it initial assessments is something that is easy to realize and it is affordable by the local company in the local context where we are working? That is my first question. And yeah.
Which one? Sorry. So you're currently, yeah.
To realize this conceptual model.
Oh, yeah.
Think it's
Yeah.
is something that is easy that
Absolutely. No,
okay.
absolutely. It's a cheap thing to do. It's much cheaper than field work to be able to just gather some of the existing information available and to using that sketch out a conceptual model. I would be asking those contractors who are doing that work to do that, because it demonstrates then to you what their real understanding is of the subsurface and the geology and what they're actually trying to do in terms of their field investigation work. I mean, we're going to go on in the next section to how to, I assume it's 1D electrical resistivity that this contractor is using that you normally engage with. Is that correct, Boris?
Yes.
Yeah. So we're going to go on to talk about how to, what a 1D sort of field program could look like, depending on the geology of the area, but focus on crystalline rock. I'm not sure what the geology is within your area that you're normally working. But yeah, having a basic conceptual model of that, of the including the identification of potential fracture systems before they carry out the survey would be, I would say, almost necessary. Otherwise, fundamentally necessary in order to carry out the survey properly. But we're going to go on to that, so I think that might help to answer that question a bit more. Any other questions? Okay, well, I don't know.
We can do
90 with
5 minutes. Yes, we can do
Yeah.
5 minutes little break. Yes, and then we come back for, I think it's a good moment to, yeah, 5 minutes. So you guys turn off the cameras. When Joan will turn on his camera, we restart. Yeah.
Okay. Thank you very
Awesome.
much.
Thank
Cheers.
you
Okay.
so much. It's very good. Thank you for the pace. It's perfect.
Good.
Thanks.
See you in a second.